So we are starting with very fundamentals of probability theory, and we were on this slide last time. We defined the mean as the area, basically expected value of x. In case of continuous variable, you do by integration, and in case of discrete variable, you do it by summation. So probability of value being xi, you multiply that and you get that thing. Similarly, variance is actually the distance from the mean, and so the variance is the expected value of x minus mu whole square. So either you do in the case of discrete variables by probability, or in case of continuous variable by integration. The standard deviation of variance is what? What is the standard? Sorry. The square root of variance is standard deviation, and so the coefficient of variation is standard deviation upon mean. Now, generally in our work, we prefer coefficient of variation to variance, and we prefer coefficient of variation to standard deviation. Let me tell you why. Suppose x is in instructions per second, IPS. Then the mean is in what unit? IPS. Okay. We could call it MIPS, million instructions per second, just to be familiar. So what would the variance unit would be? Square of instructions per second, right? And so if your mean is somewhere around 1 or 2 MIPS, the variance could be square of that, something in the, and if suppose your mean is 10, this variance could be 100. That sounds too big, first of all. Second thing is, if you change that unit from MIPS to IPS, so now your mean is in something like 10 raised to 6 something, and variance is 10 raised to 12 something. So it's totally unimaginable. It's not really easy to grasp. So standard deviation is better than variance because at least it is in the same unit. So you can say, well, the mean is 10 and the standard deviation is 5. Same unit, right? Comparable. But coefficient of variation is better because coefficient of variation has no units. It is dimensionless. So whether you measure it in IPS or whether you measure it in MIPS, coefficient of variation is 0.2, period, done. Okay? So it does not depend upon the unit. And it will be the same regardless of what you measure the mean in. And therefore, it is very easy for us to guess that 0.2, whether it is low or high, it is normalized by definition. Right? Now, I am not going to say whether 0.2 is low or high. Why not? Can anybody guess why 0.2 could be low or could be high? What does it depend upon that 0.2 is too high a variation?
Depends on what the mean is.
Well, it's not a mathematical answer. Yeah, it depends upon the system. See, the thing is, in some cases, a small variance can cause a lot of money. Think about flying, security, anything that, throwing a bomb or something, if you are off by a centimeter, you kill children, and so, you see what I mean? So the idea is that the variance, how much variance is acceptable depends upon what effect does it have on the system, what system does with that error, right? So mathematical books will tell you 0.2 is small or 0.1 is small or less than 1 is small and all that. That is only for mathematicians. In the real world, you have real dollars which depend upon that number. Okay? So in some cases, 0.2 would be considered small. In many cases, it would be considered very large. If you are off by 20% when throwing a bomb, you would be fired right away, right? So that's the situation, okay? All right. Let's move on to the next thing. Oh, actually, this is just an example of the previous thing. So we had the example of the distribution, and that was uniform distribution. Remember the uniform distribution from 1 to 3. So minimum is 1, maximum is 3, and the probability is half anywhere in that range. So if you want to calculate mean value, then you take the expected value from minus infinity to plus infinity, x times fx dx. Now minus infinity to plus 1 up to 1, it is 0 anyway, so you don't need to worry about that. And from 3 to plus infinity, it is 0, so you don't need to worry about that. So you really need to take the area under the curve between 1 and 3. And the area under the curve x times fx. Fx is half in that region, times dx. Now you will have to know integration, differentiation, and all of those things. So if you do integrate x upon 2, the integration is x square upon 4, and then you put number 3 there, you get 9 by 4 minus, then you put a 1 there, you get 1 by 4, and the mean is 2, which is what you could have gotten without too much mathematics. I mean, if your thing is uniformly distributed between 1 and 3, the mean is 2. Right? But this is a very simple distribution, and in other cases you really have to use the formula. All right, so we found the mean. The variance is xi minus mu whole square fx dx. So xi, actually from minus infinity to plus infinity, I shouldn't put xi here, it should be simply x. This is not a discrete variable, so can I take it? Just a handout. And so basically you put x minus mu is 2, so x minus 2 whole square times fx is half dx from 1 to 3. Now x minus 2 whole squared, if you integrate that, it becomes a cube by 3. So that becomes x minus 2 raised to 3 divided by 6. And now you put x is equal to 3, you get 1/6, minus, you put minus 1, and that becomes minus 1 upon 6 plus 1 upon 6 gives you 1/3. So the variance is 1/3. Everybody feels comfortable doing this integration differentiation? Okay. All right, since this is 1/3, the standard deviation is square root of that, 1 upon the square root of 3. The coefficient of variation is sigma upon mu, which is 1 upon the square root of 3 divided by 2. So 1 upon 2 times the square root of 3. All right, this time I am skipping this, but from next class onwards, we will have actually what we call mini quiz, which means that right after such examples, I will ask you to do something right there in the class, so you get used to doing this right there. Okay. So anyway, and that way it will help also if you ever done it before. But anyway, let's move on to this next one. So next one is covariance. Covariance has to do with two variables. So far we are talking one variable. Now we have two variables, x and y. Both of them are random, but they are somehow related. And therefore the covariance is the expected value of x minus mu x times y minus mu y, expected value of the whole thing. It is denoted by sigma xy. And if you multiply these two, you would get basically expected value of xy minus expected value of ex ey. So that is basically, this is mu x and this is mu y. So this is expected value of xy minus mu x mu y. And you can do that basically very easily, because what happens is if you multiply this, you will get 4 terms: xy minus mu xy minus mu yx and minus mu x mu y, right? 4 terms, and you take the expected value of each of those, and basically everything will cancel. The 2 terms will cancel out, and these 2 will be left over. Basically, this term will appear 3 times, minus plus something like that. So you will end up with minus. Anyway, for independent variables, if the variables x and y are independent, then the covariance will be 0. The expected value of x times y will be exactly equal to expected value of x times expected value of y. There is no relationship. Okay, so this will be equal, that means this will be 0 for independent variables. Now, this conclusion is only one way. If the variables are independent, then the covariance is 0. If the covariance is 0, does not mean that the variables are independent. Okay, the variables could be dependent, but the covariance could still be 0. So this is just one way. Although independence always implies 0 covariance, the reverse is not true. So simply because exy equal to ex times ey does not mean they are independent. And this is the problem, that there is no test in the world for independence. You cannot prove statistically some things are independent. Only thing you can do is keep proving that they are not dependent by this method, not dependent by this method, not dependent by that method. So there are several tests for dependence, and you can pass all those tests. More tests you pass, more you feel that you are getting too close to independence. But that's the only limit. And basically, you cannot conclusively prove that things are independent. Alright, so all the tests are designed for dependence, not for independence. Okay, so there is one test for dependence, is this one, which says that if the dependence depends upon covariance, and so correlation coefficient. Now, so now this has a unit. If x is measured in something and the y is measured in something else, this has a unit of product of those 2 units. If x and y were both MIPS, then this will be MIPS squared, just like variance. So we need something which does not have a dimension, and that is called correlation. And the correlation is simply this, which is actually denoted by sigma. Sorry, this is denoted by sigma square x by. So the top letter, this would be sigma square x by. Okay. So the top letter is sigma square x by. So you get then that whole thing divided by sigma x sigma y, which is the variance of x and variance of standard deviation of x and standard deviation of y, not the variance square root. So this is dimensionless, and not only dimensionless, this is also bounded between -1 and +1, as opposed to the variation coefficient of variation, which is not bounded. Coefficient of variation could be anywhere from 0 to infinity. Okay, this one is always between -1 and +1, and obviously 0 means not dependent. -1 means perfectly dependent in the opposite direction. So if one goes up, the other goes down, and +1 means perfectly dependent in the same direction. So if one goes up, the other goes up. Okay. All right. Dependent only. We are not talking about independence. I'm sorry. If I say independent, perfectly dependent. Yeah. And now this correlation is always misused in many fields. Like they will say, well, you know, I mean, and I have to think of this live right now, an example, and you can probably think of an example in news media. They come up with that, you know, they found out that this thing depends upon something else, right? Or I'm just going to make it up. Your chance of getting cold depends upon your hair color. All right. So how does it happen? Because they took 50 people, took their hair color, and took how often they get sick, or, you know, or get cold, and there is a correlation. Correlation does not imply dependence. Dependence implies correlation. If two things are dependent, they will be correlated. But if they're not dependent, still there could be correlation through third variable. And through third variable means that that x depends upon z and y depends upon z, but x and y do not depend upon each other. So it's not a transitive relationship. Is that people who have certain color, they use certain chemicals, okay, and those chemicals could be causing the problem, right? So, you know, I mean, like I hear one day they say, oh, coffee causes cancer, and the next they say, no, coffee improves the chances of not having any cancer. You know, similarly for heart attack, you know, everything, you know, that was supposed to happen last year, it doesn't happen this year. That's a different sample, it's a different conclusion. All right, and so be careful when you really, it just gives you some indication that there is a dependence, and then you have to really go to the system and find out. Mathematics cannot tell you the answer. Okay? All right. Correlation. Now we go into more than two variables. So if we have k variables, x1, x2 through xk, and we take some weights a1, a through ak, then the expected value of the sum is equal to the sum of the expected values. All right. Expected value of a1 x1 plus a2 x2 plus ak xk is equal to a1 times expected value of x1 plus a2 times expected value of x2, and so on and so forth. This is always true, regardless of dependence. But if you take the variance, then the variance will also add up only if they are independent variables. If there is a dependence, then it doesn't add up. Okay, only for independent variable, variance of a1 x1 plus a2 s2 plus axk would be like that. All right, then we move on to the next concept called quantiles. And the quantile is like percentile. You all have heard of percentile. The real statistical term is quantile. So the quantile is actually measured between 0 and 1. So when we say 0.9 quantile, we mean 90 percentile. When we say 0.95 quantile, we mean 95 percentile. Okay, so the quantile is measured between 0 and 1. Percentile is measured between 0 and 100. And so when we say that the alpha quantile, we mean 100 times alpha percentile. So alpha is generally 0.9 or 0.95. So we talk about 90 percentile and 95 percentile. Okay. So that is basically the value at which the cumulative distribution becomes alpha. So this is our cumulative distribution, and if we draw a line at 0.75 and we read the value of x, at that value 75% of the values are less than that value, right? So that is the 0.75 quantile of x. If we take 50% and we draw a line at 0.5, so that is the 0.5 quantile or 50 percentile. Similarly, you have 0.25 quantile or 25 percentile. Now looking at this graph, which is the density function, it's kind of not easy to say this thing, but basically all it is saying is that the area under the curve on this side is equal to the alpha. So when you take 75 quantile, 75 percentile and draw a line, then the area under the curve is 75%, which is 0.75. Alright, so there are some special names for these quantiles. For example, the 50 percentile is called the median, and then this is called quartile, Q-U-A-R-T-I-L-E, quartile. So this is the third quartile, second quartile, first quartile. Quarter, 1/4. Alright, so we have first quartile, second quartile. So you are in the first quartile, means you are in the bottom 25%. You are in the top quartile, means you are in the top 25%, right? So this is these are quartiles, and the median is the medium on the 50 percentile. And mode is the value at which the density function is maximum. It has nothing to do with this one. Basically, this is the point at which the slope of the distribution function is maximum. The slope is maximum, so you cannot really see the slope that easily. But on this graph, you can see, because this is simply the slope, right? So the maximum point is called the mode. So the mode of x is this value. Alright, so everybody understands now quantile, percentile, quartile, median, mode. Then we move on to normal distribution. Now, the normal distribution is this function. Density function is 1 upon sigma square root of 2 pi e raised to minus x minus mu whole square upon 2 sigma square, and it goes from minus infinity to plus infinity. And it's very, I mean, like, you never really use this expression for anything because it's very difficult to handle this expression to begin with. But this is the most common distribution. That's why it is called normal distribution. So you take any random numbers from any distribution, but take a lot of them. Take a lot of them, then the sum will be in most cases. Now here's the thing, there are few exceptions which we'll talk about towards the end of this class. But for most cases, for almost all cases that we generally deal with, the sum is normally distributed. This is also called the bell-shaped curve, you know, or so the thing is, the name normal simply means that this is what normally happens, is that, you know, you take any distribution and you take a lot of numbers, add them up, and take the mean, and therefore the mean is normally distributed. So the mean from any distribution is normally distributed. Okay, let me qualify basically this one, because some people will start. So in what cases would the mean will not be normally distributed? So there are exceptions when the variance is infinity. Okay, and we will not really encounter those most of the class. At the end of the class, we'll talk about that in the end of this whole semester. What are the variables that have infinite distributions? In infinite variance. Okay, generally we don't encounter them here. So for everything, basically the mean is normally distributed. A normal variate, so we do use the notation, and that is the most important thing, is that instead of writing all this, we call it n mu sigma, where mu is the mean, sigma is the standard deviation. And if it is 0 and 1, which means the mean is 0 and the standard deviation is 1, we call it a standard normal distribution, and we use our unit normal distribution. And we are going to use it very much throughout this book, throughout this chapter, throughout this, not chapter, throughout this course. Unit normal distribution. A unit normal distribution is one which has a mean of 0 and the standard deviation of 1. So if you go to another example of normal distribution is, if you go to a toll booth, the cars are coming 15 lanes, and there are 15 of those toll booths. Generally, there are more cars in the middle and less cars in the extremes. That's the normal distribution. Or if you throw some things, mostly the things will fall mostly in the middle, few will go on the sides. That becomes a normal distribution. So bell-shaped curve happens many places. All right, quantiles. So normal distribution also has a quantile, and we are going to use those. We call them Z, the letter Z. So the alpha quantile of normal 0, 1 is called Z alpha. And if it is not normal, then it also has the quantile, and that quantile is equal to mu plus Z alpha times sigma. So if it is 0 and 1, then it is exactly equal to Z alpha, otherwise it is mu plus Z alpha sigma. So what that means is that if you want to get the quantile of a standard normal distribution, you can just read it from the book. At the back of the book, which some of you have, at the back of the book, there are tables A1, A2, and A3 about the normal distribution. Okay, page 628 onwards. So A1 has the area under the curve, A2 has the quantiles of the unit normal distribution, and A3 is the commonly used values. Let me go through the commonly used values. So 99%, which is 0.01 quantile, is not 99. Actually, let's talk about 95 level, which is 0.05, is 1.96. All right, and we remember this because we need that number so often that after certain use you will also remember this. Right now you may not, but 1.96 is the 95 or 0.95th quantile of normal 0, 1. Okay, but if you don't have normal 0, 1, you have some other mean and some other standard deviation, then all you have to do is take the mean plus 1.96 times whatever the standard deviation is, mean plus 1.96 times the standard deviation, you will get, for that variable, the probability is 95%. Okay. So there are two reasons for the popularity of the normal distribution. First is the sum of n independent normal variables. First of all, the normal distribution is good in itself. You take one of them, it is normally distributed. You take two of them, the sum is normally distributed. You take three of them, the sum is normally distributed. So you can take any number of normally distributed variable with different mean and standard deviation, of course. The sum is normally distributed. So very easy to handle. When things add up like that, it's very easy to handle. Mathematicians like it. But it's not just by itself, it's also that you take any distribution and the sum has a normal distribution. All right, and this is called central limit theorem. Okay, central limit theorem says that when you have a lot of numbers from any distribution, the sum is normally distributed. And that's why the experimental errors are normally distributed. Because you have taken care of all the factors, but there are lots of other parameters that you have not taken care of, and they are causing the variation in your measurement, and therefore the errors are normally distributed. They are at least assumed to be normally distributed. And in our class, we'll learn how to verify that assumption, that something is normally distributed. Okay, but the reason they are assumed to be normally distributed is because they are caused by many, many factors. Each factor gives a little variation, and the sum of all these variations becomes normal. Yeah.
So if you've got a non-normal distribution, that would be a sign that something wasn't right in your experiment.
Yes. So then we will change the model. That's the whole purpose of this course actually, is that we emphasize that you have to verify all your assumptions. And one of the things we teach you later on in the course is how to verify these assumptions in a manner so that even your manager can understand everything visually. So we use statistics, but only to the extent that it makes sense.
Right.
Yeah, if it is not normally distributed, then the model is not good. All right, so first you have to understand why we assume normal is because it is the sum of many, many things that we don't know, right? Okay. So here's first homework. And this will be due next Monday. The execution time of queries on a database is normally distributed with a mean of 5 seconds and a standard deviation of 1. So the mean is 5, standard deviation is 1. So now you have to find out what is the probability of execution time being more than 8 seconds. So you need that table. In that table you have to figure out where it will happen, what quantile it will happen, and that is what we are asking. What is the probability of execution time being less than 6 seconds, which is a similar question, but we are asking on the less side, less than 6 seconds. So you have to just measure from minus infinity to 6. In the previous case, you are measuring from 8 to infinity. More, this is less. What percent of responses will take between 4 and 7 seconds? So now we are asking what is the probability of being 4 and 7. So, we are not taking minus infinity or plus infinity, we are just taking from 4 to 7. Again, that table will help. What is the 95 percentile execution time? So again, you have to find the 95 percentile, and given, if you remember the number 1.96, you can do that right now in your head from 1.96. The reason you need that table is because you can't remember the rest of the table. Okay. Does everybody feel comfortable doing this homework? Any question about this? All right. So now we move on to a totally different topic. So this is actually, in some sense, so far what we did was what we call prerequisites. That is something that I assume that you already know. And now I'm trying to introduce something that you may not know. Hopefully you probably know this too, but this is little bit now getting out of the prerequisites. And so first thing is that if you have so many numbers and you really can't present all the numbers to somebody, because you can't, nobody wants to listen to 1500 numbers. So you need one number. The best you can do is summarize the whole thing by one number, just one number. So what that number is, that number could be the mean of all those 1500 numbers. It could be the median of all those 1500 numbers, or it could be the mode of all those 1500 numbers. Mean, median, and mode. So how do you get, so now another term we are going to use is sample. So really, what happens is we use the word mean in a statistical sense, which means in a theoretical sense, which means that if something is normally distributed, we say mean is mu, and if you take one number, you just take one observation, that will not be mu for sure. Right? If you take 2, the average of those 2 will not be mu either. Right? If you take 3, the average will not be mu. If you take maybe million, maybe the average will come close to mu. Right? So this average of million is called the sample mean, because your sample is a million observation. And the real thing that you are looking for is called the mean. That is what we call population mean. We don't use the word population, but that is really, if you took infinite observations, then you will get to the population mean. Right? Otherwise, every mean that you get by measurement is a sample mean of a different sample size. The sample size increases, you get closer to the population mean. So understand the difference between the population and the sample. Right? Sample is a small subset of the population. So when you hear a survey on the TV, they say that 55% of the people are supporting candidate X, 45% are supporting Y. That's a sample observation. Right? They took a small sample and they're making a prediction about the population, whole 300 million people in the United States, which obviously they cannot sample. So the thing is, we are going to sample mean. So sample mean is obtained by taking the sum of all observations and dividing the sum by the number of observations in the sample. That number that you get, we call average, is the sample mean. Sample median is obtained by sorting all the observations in an increasing order, sort them out, and take the middle number. If the number of observation is odd, then you can take the middle number. If the number of observation is even, then you can take the average of the two middle numbers. Right? Sample mode is obtained by plotting a histogram and specifying the midpoint of the bucket where the histogram peaks. So you really have to draw a density function kind of thing, histogram, and wherever the highest, most common thing is, that is your mode. Mode is the most common thing. And so this is done for categorical variables only. Actually mostly for categorical, not only. For mostly for categorical variable. If now remember what is a categorical variable, suppose you have CPU type, 86, x86, x, AMD or whatever, and you have some numbers, and then you are interested which is the most common. Alright, whenever I go shopping, I always look for most common. Because why? Because if million people have tried it and then this one what they liked, maybe there is something in it. Right? So Amazon allows you most popular, most positively reviewed, cheapest, and so on and so forth, right? And so you have to look through many dimensions. One dimension is most popular, which is the mode. Yeah.
What's a categorical variable?
Okay, so categorical variables, remember there were 4 types of variables, quantitative and qualitative. Among the quantitative variables, we had discrete and continuous. Among the qualitative variables, we had ordered and unordered. All right. So everything that is qualitative is categorical, whether they are ordered or not ordered. Okay. That means there are certain number of values they can take. If those values indicate some order, then we call them ordered categorical variable. If they don't indicate, so CPU type is a categorical variable, right? Another categorical, so for example, number of disk in a CPU, in a computer, or number of USB port in this laptop, that is what kind of variable is that? Anybody? Number of USB ports? Huh?
Quantitative.
It's a discrete quantitative variable. It cannot be 2.5. It has to be 2, 3, 4. All right? And even for that, actually, so let me correct myself. Even for that, we could go for the mode. Mode is basically, so what is the probability of one port being is 10%. Very few computers will have one port. 2 is very common, probably the mode. 3 is less common, and 4 is even less common, and 5 is even less common. Right? So categorical variable is basically the categories. Yeah. So that is, in fact, it will apply to both the discrete, continuous, as well as qualitative variables. All right. So mode. So we understand how to get the numbers, right? Mean by adding, median by shorting, and mode by finding out the most common. Now, mean and median always exist and are unique. Mode, on the other hand, may not exist. So why they will not exist is because like this. Suppose you have a distribution which has 2 modes. Well, all right, so it's not unique. Now for this distribution, the mean is here, the median is here, and the mode is here. This is a very symmetrical distribution. This distribution, same thing. There is a mean and median, but there is no mode, because there is no point at which this is higher. For this distribution, the mean is here, the median is less, and the mode is even less. Okay? And for this distribution, the mode is here, the median is less, and the mean is less than the median. So all possibilities are there. The mean and median could be on any side. Here, in this case, the median and mean were here, and the modes were many of them, and here 0 mode, there's many modes, and so on. Now, which one of these numbers is the right number? Again, I'm going to give you guidelines, and you can change those guidelines. You can change those guidelines to suit yourself when you feel that something is more appropriate. And there are cases when you will come up with saying that, well, I don't think this flowchart applies. I'm going to give you a flowchart which should get you to the right places in most cases. But again, like any other art, there are exceptions. Okay? So the science part is here. But again, the science does not do everything. So first, is the data categorical? If it is categorical, you probably want to use mode, because saying that the median is AMD CPU, nobody cares for AMD CPU if it is the median, right? Probably people want to know what is the most commonly used CPU, right? So use the mode for categorical variable. Is the total of interest, sum of these numbers, whatever number we have, would somebody be interested in the sum of 1500 numbers? If yes, then mean is the right thing to do. Again, the right is with a qualification that generally the right thing to do. Okay? If the total is of interest to nobody, is the distribution skewed? Skewed means it's not symmetrical. If it is skewed, then use median. Otherwise, go back to the mean again. So mean can be used in 2 different cases, either because it is sum is of interest, or because nothing else fits. All right. So categorical means we generally need the most common option. And that's why actually, I mean, I keep giving examples of Amazon, but basically Amazon has a list of they have a list of top 100 of every thing that you're looking for. So if you're looking for something, you go to the top 100 list, find out which is the most common, which is the second most common, which is the third most common, and so on and so forth. Okay? And that is of some value, that information. If it is not categorical, then sum of interest. So we will take an example that will make it more clear. Here, most used resource in a system. So we have many things in a system. We have CPU, we have a disk, and we have memory, right? And then we want to find out which is most used, right? And here the resources are categorical, and therefore the mode must be used. So we just want to know whether the disk is problem, or it is the network which is the problem, or the memory is the problem. So we will use the mode. Inter-arrival time. So we want to know the inter-arrival times of requests. Now, if you add up all the inter-arrival times, the first person came, after that 4 seconds later the second request came, then 4 seconds later third request came, and the sum of these is the total time interval that you measured. So it has some physical meaning, and it is of interest, and therefore mean would be the proper choice. Load on a computer. So you measured the load, it came out 1%, then 3%, then 5%, and so on and so forth. Now if you add up all those percentages, does it have any meaning? It doesn't have any meaning, by the way. So if let's just take two examples. So I measured first hour, it is 25%, second hour it is 50%. So the total is 75%. It has no meaning really, because what do you do with it? So unlike the inter-arrival time, where now this is a difficult concept. When I say it has a physical meaning, you really have to do lots of exercises like this to get used to what is the physical meaning means, and then it will click to you right away that yeah, total is of interest, the total is not of interest. So in this case, the total is not of interest, and therefore median is preferable. And second thing is also it is very highly skewed. So most of the time when you talk about the load, systems are always most likely very lightly loaded. So 95% of the time there is nothing going on. 5% of the time there is a big load. Right? So this is very highly skewed. Average configuration. So if you want to find out what is the average configuration of a PC, you will indicate the medians of the number of devices, memory sizes, median, number of processors are generally, again, median, due to the skewness of the distribution. So you will just mostly use that. All right. So what we have done so far is, let's just review that, is that if you need to summarize a lot of numbers, then you see whether it is categorical or not. If it is categorical, then use mean and mode, otherwise mean. And if it is total is of interest. If this distribution is, actually this one is, if the distribution is not skewed, then it doesn't really matter whether you use mean or median. Because if they are not skewed, means they are equal. Right? Notice this. If the distribution is not skewed, like this one, median is equal to median is equal to mean. Like this one, median is equal to mean. Only when the mean is not equal to median, we call it skewed. So you use the mean. But if somebody says, how come you didn't use the median, then you can say, well, it's the same number. The distribution is not skewed. All right. So that, we are going to change the topic. Before I change the topic, any questions about selecting between the three? So let's go to the misuse of means. So while you want to take the mean of 4, 5, 6, 7, you don't want to take a mean of 4 and 500. They are very different numbers. Okay, anytime you find yourself adding very different numbers, you know that something is going wrong. And that is one of the tests we will do throughout this modeling thing, is that we notice what is the range of the numbers we are adding. Okay, and so for example, if we have numbers like this, a system A we measured for 10 hours, whatever we measured, I don't know what we are measuring here, but the number came out 10. For system B, number 5, 9, 5, 11, 5, 10, 4, 10, 31. Now these numbers are all between 9 and 11, 9, 10, 11, 9, 10, 11. So the sum is 50, the mean is 10, and the typical value is 10. In this case, the sum is 50, the mean is 10, but it has nothing to do with the typical value. Typical value is 5. Yeah. Well, I mean, typical value actually is not the mode, but here you can see visually that typical value generally it is 5. That's what I mean. I'm not meaning in the statistical sense. I mean in the just visual sense. The typical value is 5, right? So this mean of 10 is not really meaningful because that is misguiding. That my performance is 10. Your performance is really 5, except in one case that you got 31. So that is one problem. Second problem is when you are adding the number, take the minimum, which is 4, and take the maximum, which is 31, take the ratio, which is 8. 8 is probably okay. But if it is any time more than 10 or 100 or something, the higher the number, the ratio, minimum min-max ratio or max-min ratio, you know that you are in trouble. I mean, in case of by adding that number, by adding those numbers. Okay. All right. So first thing is that you don't want to add numbers which are very different. Second thing is multiplying. So EXY, the product, the mean of the product is not equal to the mean of the means, product of the means. Mean of the product is not equal to the product of the means. It's only equal in the case of what kind of variables? Independent variables. If x and y are independent, then yes, EXY equal to EX times EY. If they're not independent, then this is not equal. So you cannot do that. So on a time sharing system, the average number of users is 23. The average number of sub-processes per user is 2. So the average number of sub-processes is not 23 times 2, 46. Because that there is a correlation between these two. If the number of users is high, people don't span many sub-processes. On the other hand, if there are no other users, we do 1500 things at the same time. So they are correlated variables particularly. So you cannot just multiply the two means to get the total. All right. Second, taking a mean of a ratio with different bases. So we saw ratio games, and we saw that every time the denominator is different, then you cannot just add them up, those ratios. Right? So this will be discussed a little bit more later on, but right now you understand that if you are taking you're adding up the ratios, and if the bases are very different, then that is you are getting into trouble. Now mean itself is of many different types. First, there is arithmetic mean that we just saw a minute ago, that is simply adding the numbers, but then there is also a geometric mean. Geometric mean is obtained by multiplying and taking the nth root. Okay, and it is used if the product is of value, product is of interest, and we'll see examples in a minute. So the performance improvement in 7 layers is as follows. Now 7 layers of a networking protocol. In computer networking we talk about 7 layers. So the first layer we improved by 5%, second by 28%, third by 40%, and so on and so forth. So what is the total improvement? Okay, to find out the total improvement, this is like basically what you have to do is, if the performance was 1, With the new first layer, now we have 1.05 performance. With the second one, we have 1.28 times better performance, and so on and so forth. So we multiply these numbers 1.05, 1.28, 1.10, 1.08, and so on and so forth, and take the seventh root, we will get 1.13 minus 1 is 0.13. So 13% is the average improvement per layer. You cannot just add up these numbers and divide by 7 to get, because these are ratios, by the way. Remember, percentages are ratios, right? So that is one thing that you will notice in this case is, oh, these are ratios, so we cannot just add them up. And in this case, the product is of interest. Not the product of these numbers, but the product like this is of interest. We really need to know total. If the performance was 1, and we use this system, the total performance will be basically the product of all these 1 plus those numbers, right? So that is how we will get per layer. So multiplicative matrices are very common in computer science, believe it or not. And for example, cache hit ratios. So you have level 1 cache, level 2 cache, level 3 cache, different levels, they all multiply. Cache miss ratios, same thing, hit ratios and miss ratios. Percentage performance improvement between successive version. So you have version 1 of a program, and then you improve by 10%, and you take number 2, version 2, and version 3, you improve by another 15%. What do you have to do? You have to multiply and take the root. Average error rate per hop on a multi-hop path in a network. Same thing on a network, you are going every hop. First hop you did 10% better, second hop you did 20% better, and so on and so forth. You have to multiply and take the mean. So these are examples of multiplicative means. Now if you have ratios and you want to take geometric mean, then the geometric mean actually turns out to be either way you do, it's okay. So you take a geometric mean of these numbers, you can take the geometric mean of the numerator, divide by the geometric mean of the denominator, or you can take 1 upon geometric mean of the reverse. They all work out the same number. So the geometric mean of a ratio is the ratio of the geometric means of the numerator and the denominator. The choice of the base does not change the conclusion. And because of this property, sometimes mathematicians recommend that whenever you have a ratio, you should do geometric mean. Okay? But it turns out that that is not always the case. Basically, there are cases where you really have to think about whether the numerator and the denominator have any physical meaning. For example, if I gave you geometric mean of x's, are you interested in that for any reason? If you're not interested or nobody is interested, then this ratio, geometric mean ratio doesn't make any meaningful thing. So it's little bit complicated stuff than just making that always, for ratio you take geometric mean. Finally, there is one more mean which is called harmonic mean. Harmonic mean is just the mean 1 upon n, 1 upon x1, x2, x3. You take all of those, sum them up, and divide by n, and then do 1 upon that. So it's basically defined by this formula, geometric harmonic mean. And this is used whenever the arithmetic mean can be justified for 1 upon x. So elapsed time of a benchmark on a processor, elapsed time themselves don't add up, but if you take 1 upon those, they add up. In the ith repetition, the benchmark takes ti seconds, and so suppose the benchmark has m million instructions, so then the xi from the ith repetition, the performance is m instructions divided by the time. This is the MIP rating, and then you get the second one, second observation. The m doesn't change, but the ti changes for the second benchmark. And ti changes because this is a random number. Every time you do it takes different time for the same benchmark. So the m remains the same, but the time is changing. In this case, you cannot give the average time simply by adding. You should do because that has no physical meaning, but this one has a physical meaning, 1 upon Ti, physical meaning, or m upon Ti has a physical meaning. And so you would use the harmonic mean for this particular number. So average MIPS for a processor is basically you have to divide by, again, same way. So you will get this way. Okay, so this is actually a case of an example where you did not, even though this MIP is a ratio, you did not take the geometric mean, because we have m divided by T1 through Tn, 1 upon n. This is not a geometric mean. And so this is more of a counterexample to the common advice that for ratios you should always take geometric mean. And so, and therefore this is a preferred metric here, m upon 1 upon n, T1 through Tn. If m's were different, then you would do it like this. You will do this arithmetic mean on the top and the arithmetic mean on the bottom. Now similarly, weighted or harmonic mean is defined as with weights W1, W2 and so on and so forth. I don't think we will use it that much, but just just to complete that, there are other means. If all the weights are equal, then we call it harmonic mean. If the weights are different, then you would get for example, in the case of benchmarks, we will use weight proportional to the, we could use a weight proportional to the number of instructions in that benchmark. If it is a small benchmark, it is a small weight. If it is a large benchmark, it is a large weight. And so then you would get similar to what we did before, sum of all the instructions divided by sum of all the times. So now let's go to the ratios. If you have the ratio A1 upon B1, A2 upon B2, all the bases are different. And so the question is, what is the right way to do it? So there are many cases. If the sum of the numerators and the sum of the denominators both have a physical meaning, the average is the ratio of the averages. Now here is the thing, basically, is that is anybody interested in the total sum of A's and total sum of B's? If they have some physical meaning, then you can just sum them up and take the ratio, which is equal to saying that we take the ratio of the means. Okay, I will give you an example in a minute, but is this thing clear what we are saying? Is that if you want to take the ratio, mean of a ratio, then first question to ask is the numerator sum and the denominator sum is of interest. And so here is an example. We measured the CPU utilization for 1 hour. The busy time was 45%, second hour 45%, third hour 45%, fourth hour 45%, and then for 100 hours it was 20%. If you just add up like this, the sum is 20%, 200, and divide by 5 is 40%. Is that the average utilization? No. Average busy time? No. Or average busy percentage? No. Basically, the right percentage is to add up the total measurement duration and the total busy time. Total measurement duration is 104 hours, and you have to figure out how much this CPU was busy for in those 104 hours, and that will give you the right utilization over 104 hours, right? So to do that, it was busy for 0.45 hours in the first hour, 0.45 hours in the second hour, and so on and so forth. You add up and you get 21% as the mean CPU utilization. So in this case, the total sum of the CPU busy time is of interest, as well as the total sum of the time is of interest, and therefore we just do it numerator and the denominator separately. And therefore we see this thing that the ratios cannot always be by geometric mean. Okay? So this is more complicated than just geometric mean. A geometric mean of utilizations is useless, as we saw. Okay. So now the key question is, when do you think something has a physical meaning? And as I said again, I will emphasize this time again, is that first in the beginning it will be wrong sometimes, but after doing several examples, several exercises, you will start getting the feeling as to, is this sum has a meaning. So there are some special cases. If the bases are all same, then it's very easy, because if the bases are all same, then all you have to do is just add up the numerator or take the mean of the numerator. And so if you have this resource utilization which are measured over the same period, not 1 hour and 100 hours, everything is on 1 hour, then you don't have to work very hard. You could just do the arithmetic mean. If the denominators, if the sum of the denominators have a physical meaning, even though the denominators have different values, but the sum has some physical meaning, then you would basically use this kind of formula where the average is the sum of the numerator and the sum of the denominator. Another way of saying this same thing is to say that we do the harmonic mean of the ratios. Okay, these are the ratios A upon B1, we take the harmonic mean. Do the harmonic mean, we do B1 upon A. B2 upon A, and so on. Add up, divide by n, and do 1 upon. So same thing basically. Okay, so in this case the denominator have a physical meaning, and that's why we need the harmonic mean. If the numerator and denominator are expected to follow a multiplicative property such that AI is generally equal to C times BI, where C is approximately a constant and is being estimated, then C can be estimated by geometric mean of AI BI. So that's the thing, is that if that there is a multiplicative relationship, then yes, then you do geometric mean. And so example is a program optimization. Just like we thought about the 7 layers program optimization, this is same thing. If the then we could say that each thing multiplies. Another thing is that if these things are log, if the log of these things makes sense, in that case, you could just do the arithmetic mean of logs, which is same thing as geometric mean of ratios. Okay? If you do arithmetic mean on the log scale, so when you add up in the log scale, that is like multiplying in the normal scale. And when you take the average in the log scale, you are doing the geometric mean in the actual scale. So here is an example. The code size, so there is some kind of optimization technique, and they tried it on many different benchmarks. On first benchmarks before optimization, the code size was 119, it became 89, so the ratio is 0.75, and so on and so forth. So what is the average performance of this technique? And obviously, I mean, the thing to notice here is that basically we assume that the number is very close to some ratio C, which is this thing, so we can take the geometric mean and get that, assuming that one, right? Another method would have been if somebody, I mean, again, the main thing is that you have to be able to justify why you are doing whatever you are doing. So somebody could justify geometric mean by this method, that we are just following the A equal to CBI kind of formula, and there is a ratio here which is close to this 0.79. On the other hand, somebody could say, well, I think the total code size has a meaning, because that will mean that, this could be, for example, 7 parts of a program, part 1, part 2, part 3, part 4, part 5, part 6, part 7, part 8, 8 parts, and this is the total program. and therefore this is the total program length, this is the total program length after, and this is before, and therefore the ratio. However, and these 7 workloads are not like that. So, I mean, that argument could be, somebody could argue, well, look, I mean, I am interested in bubbler, but I am not interested in adding bubble to sieve. I don't use sieve at all ever. I mean, so these benchmarks are totally, I mean, you don't just add up. So, it depends upon what these benchmarks are. And if there is a reason to believe that they would add up in some situation, then we add up these numbers, and we add up these numbers, and we get the ratio that way. All right. So let's just summarize this part before we go to the next part. We talked about 3 different ways to get a single number out of a sample. What are those 3 ways? Single, we call it, we actually the name I didn't use in the class today, but that is called the index of central tendencies. Okay, it's a complicated name. And the problem with that name is nobody in the real world knows that. So you cannot just tell them, look, the index of central tendency is this. So I don't use it that much, but statisticians call it. So anyway, there are 3 indices. First one is mean, mode, and median. And there is no reason that one could not be more than the other. All right? And we saw all kinds of situations. Then we had a flow chart about how do you select between the 3. Right? Again, that's a guideline. Then we went into the mean, and we said there are 3 kinds of mean: arithmetic mean, geometric mean, and harmonic mean. And the very simple thing to remember is that if some things really naturally add and the sum is of interest, then arithmetic mean. If they naturally multiply and the product is of interest, then it is geometric mean. And if it is just the 1 upon something is more of interest than that x itself, then a harmonic mean is more interest. And we saw sort of many examples. And again, you really have to do a lot more exercises in the book and feel comfortable. The exercises are there and the answers are there in the book too. So, I mean, you can check out yourself. And we saw some examples here about different things, and in every case we have one answer, but somebody could argue for the other answers, and we have to have that is the whole thing, is that you have to have a reason for that answer. So here the geometric mean looks okay because these are very different workloads, as opposed to if there are parts of the workload, part of the whole thing, then the sum would be of interest, and we would do it differently. Okay? All right. Any questions? So then let's move on to the variability. Now mean is one number, but sometimes it is a meaningless number. And that's why this quote. Quote says, then there is a man who drowned crossing a stream with an average depth of 6 inches. Would you cross a river where the average depth is 6 inches? Depends upon what?
How deep it is in the middle.
Variability. Whether the depth is 6 inches constant or it is 6 inches and 600 feet. Right? So that's the thing, is that the mean doesn't give you all that information. So you really need to know the variability. And so the mean is here and the variability is very little, no problem. But if the mean is here and the variability is large, then mean has no meaning. Here, this is what I call mean is meaningless. Okay? So now there are indices of dispersion. So that was in indices of central tendencies. Now these are indices of dispersion, how widely numbers are distributed. The first way of indicating is a range. A range is the easiest. You tell them that, look, I took this measurement, the minimum is 5 and the maximum is 1500. So they know that this much is the variability, 5 and 1500, min and max. When you specify the two numbers, min and max, that gives you an idea of variability. Second thing you could do is the standard deviation or variance. And again, there are three ways: variance, standard deviation, and coefficient of variation. The preferable method is out of those three. Variance, because variance nobody can even guess how to interpret it. Right? Standard deviation is better than variance, and coefficient of variation is better than standard deviation. As you could say, well, the mean is 100 and the coefficient of variation is 0.2. People like us who are dealing with these statistics all the time, they will understand 0.2 what it is, right? On the other hand, range might be more easily understood by normal people who do not understand coefficient of variation. They would understand that the minimum is 4, maximum is 1500, and the mean is 200, right? So variance. Second is percentiles. So you could say, well, the lower 10 percentile is so much and 90 percentile is so much. So this is where most of the numbers are, between 10 and 90, right? Semi-Inter-Quartile Quantile range. Actually, I have a slide on each of them. So this requires a little bit more explanation than I want to do it on one slide. Semi-Inter-Quantile range, and then mean absolute deviation. So let me hold on to those two. Range. So range is max minus min. Larger the range, higher the variability. In most cases, range is not very useful. Why? Because range generally means outliers. If the maximum is 1500, it's good to know that it could be 1500, but most people are at 10. Right? And so both the min and the max keep going in one direction as the sample size increases. If you have just one sample, your range is this much. 2 samples, the range goes up and up and up and up and up and up and up. Right? And so while this is very easy to understand, and they don't need a statistical background to understand the range, but at the same time, you are losing some information. You are not really telling them that most of the numbers are here. You are just telling them outliers. So range is not very useful. The minimum comes out to be 0 and the maximum comes out to be very high. And unless the variables are bounded, the maximum goes on increasing. So if you had a normal distribution and you took 2 million samples, you will say, well, it goes from minus infinity to plus infinity. It doesn't really give you any indication. On the other hand, if you would have said that the variance is so much, or this coefficient of variation is 0.2, that is much more useful than knowing that they go from minus infinity to plus infinity. Right? So that is like hiding the information. So the variable is bounded and goes on. So basically that's the thing. Okay? Range is useful if and only if there is a reason to believe that the variable is bounded. If there is a reason to believe that this will not go above this, then you say this is the maximum. There is a reason to believe this will not go below this. So this is the maximum. This is the minimum. Okay.